Okay, we are live. So this is where we left this morning. Did you manage, by the way, to download the trial version?
Yeah, I downloaded SR27. I think Alexa.
Everything should work right now.
Yeah. It works fine. It just I get these orange pop-ups, but fine. I can.
Yeah, the orange. Yeah, never mind. That's actually because the service release 27 is actually more recent than my service release of Rhino.
Okay.
So it's just kind of whining a little bit, but that's harmless. That's a harmless message. It's just annoying that the components are orange, but it doesn't harm the thing. Okay. Any questions on this before we go forward?
For the moment.
All good.
All good? Okay. So we can open also now the 01, the heuristic setup. So for all of these definitions, you might have to tell Grasshopper to relocate assemblies DLL, but that is going to be just the first time you open them. If you save them afterwards, the next time you open the same definition on your computer, the new location will be saved inside the components and you won't have to do it again. It's just like the first time. That's because when you have to associate a library with a scripting component, there is only one way, which is through the Manage Assemblies option. And this option just allows you to record the location as an absolute path and not a relative path. So this is like how Grasshopper is built and how it manages library. So there is no way of making it a relative path, at least in this version of Grasshopper. So once you associate the DLL, you should see the same setup where we arrived up to the last definition this morning. And then there's something more afterwards, but we'll consider it later on. If you look at the Rhino screen for a second, you will notice that there's a pretty extensive table of combination appearing. So the definition basically takes all of the entire set of your assembly objects. So whenever you create your assembly object and you add them to this merge, what you are creating, this list of this particular data type, which is the assembly object, will be considered from this moment on the assembly object set, which is the set of building blocks you can play around with. So starting from a set, this component generates all the possible combinations between them, among them, and allows you to put up some filters straight away. So there are like 3 possible filters here that you can activate. So right now, these are like all the possible permutations unfiltered, which means whenever we have a handle of the same type, you will try all the possible combination, all the possible rotation when the handle is in receiver mode, and it will show you the combination on this table. And it will write you the corresponding rule in terms of syntax. So this combination that you see here corresponds to this rule. This combination that you see here corresponds to this other rule. So each rule is written in the correspondence of each graphical combination. So you have also visual feeling of what each rule does in terms of how 2 objects come together. There's always a sender and a receiver. So the pink one is the receiver and the yellow one is the sender in each combination. So it disregards in this visualization the object type. It just classifies them as identifying the receiver and the sender. But in the rule, what you see is the name of the receiver and the name of the sender written there. So let me pick in this slide. Oh, there's somebody coming in. Okay. Let's go back to this slide again for a moment. And oops, not this slide, this slide. Okay. So look at this part here, where the syntax for the rule is written. So the syntax of the rule is you got a receiver name, a vertical line receiver handle, which means this is in the rule the handle at index 0 for the component that is called stick. After the equal sign, you have the index of the rotation. So in this rule, we'll consider this handle. The stick is going to be the receiver. I'm going to attach something to his handle 0 and consider this handle in a rotation of 0 degrees. So not 0 degrees, so the rotation at the index 0, which will correspond to whatever angle you've put at the index 0 when you build the handle. Then to this lesser than character means this one, the right thing goes to the left thing. So L, this component, is going to be the sender, and I'm going to attach the handle at index 2. And the weight of this rule, after the percentage, even the rules have a weight. The weight of this rule is 0, because right now, like in the other cases, the weight is there for a purpose, but that purpose hasn't been implemented yet. So I'll show you later on what is the purpose of the weight of the rules. It has to do with the field, but it's a little bit more complicated. Let's stick to the simple things right now. So this is, in general, how a rule for assemblies looks like. If you check your Rhino screen, there's one little thing added here, just for the display. What you see in the round brackets, it's the actual degrees of rotation of the receiving handle. It's just here as a reminder. Hey, just remember, the handle 1 of your component L, the handle 0 of your component L, at the index 1, this rotation was 90 degrees, so that you remember, okay? But in writing the actual rule, this part in the round bracket will not be there, because then you will pick the rule from here. But you will see also in the effect. It's just here for completeness. So what are the filters? The filters, self-C means avoid the same type component connection. So right now, a stick can connect to another stick, and L can connect to another L. If you activate that, if you activate the toggle, then they can just connect only to other types and never to the same type of themselves. So a stick can connect only to an L and vice versa. This, as you can see, dramatically reduces the amount of combinations. Let's release this rule. The other filter is self-handle, which means an handle cannot connect to itself. So an handle used as a sender can only use any other handle as a receiver from the same kind of component or from the other kind of component. It just cannot use itself to reconnect. So if you activate that, you'll see a less dramatic reduction in the number of options. Nonetheless, there is still a reduction. So let's deactivate and get into the unfiltered situation. The last one is the symmetric rules. So there are rules that give you exactly the same result in terms of geometry, except with the sender and the receiver just swapped. The symmetric allows you to identify these symmetric results and exclude them. So you have only unique combinations. So each of these filters might be useful or might cause some limitation that you'll have to explore as you test the assemblage. So when you test the assemblage with several of these sequences of rules, you'll be able to understand, or you have to understand at some point, that sometimes the assemblage might not go forward and you get stuck at a certain number of components, and you maybe cannot understand why. But if you analyze the assembly and you analyze the rules, you might realize that this was kind of inevitable because the rules might be so strict in what they allow that after a certain amount of combination, there is just no possible other combination to go forward. We will see it when we experiment with the assemblage, with the first assemblage in a few moments. But right now, one of the things you can do is exactly try to activate or deactivate this filter and look at this table of cases, this heuristic table that is generated. Now, the table, let me release all of the filters. So we have the complete table. First of all, you can use it to make a visual assessment of all the possible combination of the components that you have designed. And the writer and the viewer, this is the writer, and that passes the heuristic string to the viewer that then generates this display. The viewer is also, no, sorry, the writer, or one of them. Anyway, one of them, I guess. Yeah, the viewer. It's actually the viewer, because the writer just writes the rules. The viewer actually enacts the combination with the objects and filters also the inconsistencies, which means if there is something, if there is a component that which geometry is colliding with another, then that combination will be excluded. So let me show you just as an experiment. If I move this handle slightly inward, like let's move it -1, it's going to mean that the handle is right now inside the component. So each time I'm trying to orient it to another handle, part of it will compenetrate to the other object, right? So all of these cases are flashing red and are now excluded from the table. So if you have, if you see some of these errors and you're not expecting these errors, then double check the positions of your handles. So if you put things back in the place they were before, the filtering doesn't happen. But again, if by any sense these are very simple geometries. If you design geometries that have a little more convolution or convexity, it might be like an object that is shaped like a C, for instance, or like a U. It might be that the object can attach, but can also, part of it can also cross the other object geometry. So to avoid this, to avoid put irregular rules or rules that bring to inconsistencies, the system can already filter them. In addition to that, now for the visualization, the simple component just extract the mesh from the assembly object. What you can do from here is either you use all of these tables straight away as an entire set of rules, or you can manually pick the one that you want. So you can visually assess the thing and say, okay, I want to use the full rules, or I want to use a manual set. So when you turn to a manual set, there should be a pre-selection already in there that appears. If there isn't, no worries. I'm going to show you now how to do this selection. To perform the manual selection, you're going to have this. You're going to have to use this little plugin here, which is the Selectable Preview plugin. So you have to activate the visualization, so enable the preview, and double-click on locked. If you double-click on locked, it goes from locked to select mode. And now you can select the meshes that you see on screen exactly as if you were selecting something in Rhino, which means if you click on an empty part of the screen, you will erase the selection. To select multiple instances, I mean, you can use Windows, or you can keep Shift pressed and add it to the selection. You can just select either one of the objects in a combination, and the combination will be added to the list. Okay, so you just look around and say, oh, I want this one. Oh, I like this one. I like this. I like this. I like that. This one. What about this one? This one. Okay. Yeah, any one of those. So when you're okay, or actually also this bunch, I like that. When you're okay with your selection, you just double click again on select. The component goes back into the locked status, so the selection is actually saved. And to avoid the visual conflict, you can disable the preview again. So now your set of combination will be comprised only of the rules that you have selected. So only the rules that correspond to the geometry that you have selected will go through the selection. Okay. So again, here you can switch from manual to full, full to manual. What you do once you are happy with your selection or happy with your rule table is we can save them as a text file. Because actually what you generate in here, if we attach a panel to this output here, is a list of strings that you can see have exactly the syntax of this one in blue, right here. This will be then interpreted by the system. And the only thing that you need, apart from this list of rules, yeah, let's admit the guy. Apart from this list of rules, the only other thing that you need to make this work is the assembly object set. So the heuristic writer and the heuristic viewer can sit in a standalone definition as long as they are accompanied by the assembly object set. So the only constant that you must have is this. Unfortunately, it's not possible to, well, not yet. Implementing it is tricky. But at the moment, I mean, you cannot put this in a data component and then copy paste it into another definition. Because Grasshopper doesn't have the assembly object type as an internal type. So unfortunately, the only thing that you're constrained to right now is to have this part of the definition repeating in every definition that you need to make the assemblage. So, but basically, I've separated the component building just for the sake of explanation. You basically have like two definitions to work with. One is the heuristic definition, and the other is actually the assemblies that you perform. Then there might be a third, which is what you do in post-processing. And that post-processing part, you can keep it in the same definition of the assemblage itself, or you can separate it. But the only thing that you have to have in every definition is this part of the assembly objects, because otherwise it cannot make sense of all the geometrical basic data. Okay, so there's already a bunch of save the heuristics in the material folder. So if you look at the material folder, there's a subfolder called heuristics. And if you look inside, there are these text files here. So you can even open one up. It's really just a list of the strings that you see. So it's a very, very simple file. Right. All in all, it's pretty simple. So there are also some manual picks, some of them more or less extended. So this file is we're going to read it back in the definition where we are doing the assemblage. I mean, if you want to keep the things together, you can even copy paste everything in a single definition. That depends on how do you want to work. The more things you put in a definition, the more complicated the canvas becomes and the more it slows down because you have to perform more things. It's always a trade-off. It depends on how you used to work. I think that just saving and loading from definition to definition, a text file doesn't really spoil the fun too much, and it's pretty straightforward. And you will see that also reading the things is not going to be painful. Any questions on this part of building the heuristics?
Oh,
Yeah, all good. Yeah, a few options here in the visualizer. You can select the number of rows in which you want to display the heuristics, and the selection will be preserved. Even if you do a manual selection, it doesn't change that. And you can change the padding. The padding is acts like a multiplier to the distance in X and Y. So pad Y to 1.5 means that the distance in Y is 1.5 the bounding box of the biggest combination. So if you put them to 1, they're going to be very close to each other. So that it doesn't matter how big are the object you design, you don't have to adjust all the time these parameters. They will just adjust proportionally to the size of your components. And also you can decide to move the entire table to a different point. So this point is internalized, but you can move it around in Rhino and the entire table will move away if you need it to in another part of the screen. Yeah, there's a little thing in here, which is a deconstructor for the rule string, but this one doesn't need the assemblies because the rule is a string and it just extracts the data from the string. So it basically just splits the string and converts things into numbers. And this is, again, the rule syntax. So just once again to remind you, starting with the receiver name, the receiver handle index, the receiver handle rotation, the sender component name, the sender handle index, and the weight for the rule. So, right, okay. If there are no further questions, let's try our first assemblage now. Let's make things work. So open up the 02, simple random assemblage. Okay, so when you open it up, the Rhino file is still collision test dummies. So it's going to be our constant file probably for the entire day. And so the first part of the definition is still the assembly object set, which is our simple set that we have created. And there's this little part here that is the part where you load the heuristics. So these two components are this one and this one. These are part of Frog, which is the collection of user objects that we've done at Codate. And they just fulfill some basic purposes, but they were interesting things. So this one basically generates automatically the grasshopper file path. So it acts like a relative path. So whenever you take your definition, it doesn't matter. So this subfolder heuristics can just be in the same folder of your grasshopper definition, and he will always retrieve the heuristic directory. This one is a directory reader, so you get the name of the files and the name of the subdirectories in every directory that you input in here. So basically, we are reading the heuristics directory to get all the file names, and we have a selector so you can decide to load progressively whatever heuristic you want. So let's load the first one, the full one, full heuristics here. It shows you the entire text file again. So where does this go? So we have our assembly object set and our heuristic string. This is an important step. So we save the heuristics as a list, also because it's easier to modify. Let's say that you want to exclude some of them at this point. You can call this list with whatever pattern you want, with a list of true, false, or select specific indexes. You can still operate a selection on the rules at this point. But then to bring them into the system, you have to transform them into a single string that is comma separated, which is what these guys do. So it becomes something like this. So it's not just one line for rule, it's just a one line where each rule is just separated by commas until the last one. Because that's the most convenient for the system. I'll explain you later, because right now we will work with just one set of rules, but the system is also capable of working with multiple set of rules at once. And then you might have a criteria for selecting which set of rules the system is working with at which point. So all of these criteria, all of these things are part of the thing, the algorithmic logic that I'm trying to pursue. And that's the essential difference between the kind of tool that I wrote, and of course I will continue writing, and WASP, because WASP at its core can act only in a couple of ways. One, it's stochastically, which is using random selection, random criteria, or you can feed it a linear set of rules, but then it can just go on and it will have still a part of randomness in there. What I'm trying to go, where I'm trying to go is, of course, we're going to start with randomness because it's the easiest criteria to implement. But at the end, the goal is to take randomness away almost completely from the entire process, which means making the system decision aware with criteria that right now there are some templates criteria, but for those of you who would like to work with it, I can also share the code and tell you where if eventually you might be able to write your own criteria. I don't know if during these 5 days there will be enough time for you to understand how the entire things work, because it's not exactly simple to explain all the mechanisms, all the internal mechanisms, but I try to put up some things that for somebody who knows a little bit about C# programming, it might not be so hard to write his own rules. But if you're not confident with that, no problem. I mean, you can still play with some of the templates that are here, and it's completely fine, no problem. So everything goes in this component. And there are several options in here. I mean, don't be frightened by the number of inputs. That's mostly the fact that in a better version of this, I shall put this in a sort of more aesthetically, let's say, proper user interface, where you can decide your parameters. But right now, all you have to do is this really ugly tower building of parameters that is this C# component. But well, let's go, before diving into the component itself, let's go into how the algorithm works, right? So the algorithm builds an assemblage iteratively, which means it doesn't decide all of the things at once. It goes one step, does some sort of operation, and the next iteration, it will start from where the previous iteration had ended. This, if you are familiar with how, for instance, some plugin like Anemone work, this is very similar to that, which means Grasshopper in its vanilla state, it's like a huge for loop. It's a huge loop, right? It doesn't matter how many components you put on the canvas. If you use just vanilla components, Grasshopper treats the data from the beginning data, does all the operation in sequence, and then you end up with a result. And every time you refresh the canvas, Grasshopper restarts from the very beginning of the initial data. It's not able to record the state of an iteration and then start again from that state and perform the actions with an updated state. You need to write your own things or use custom components, such as, for instance, Anemone. So Grasshopper in general works linearly, but you can write things or use things to work in an iterative fashion. An iterative means, like I said before, you start, let's say, at iteration 0. You do something like you place your first component in your space. Then at the next iteration, you don't start from 0 again, you start from the component that you've just placed. And then you start doing a set of operations. This operation will keep repeating constantly over time at each iteration. But at each iteration, the starting condition will have changed because then there will be the result of the previous operations. So in this case, what are these operations? Essentially, once you start your first component, then it's something that you can decide, you generally decide from the outside, okay, I want to start with type 0 or type 1. And I want to start in this position or in this other position. Once you've done this first move, the operation is, okay, who's next? What I'm going to put next? So you have to decide who am I going to place? And the second thing is, okay, where do I place it? So this is, in general, the set of operations. Then once you've decided both, okay, I'm taking this one from the set and I'm placing it in that position. Done. Next operation, now I don't have one component, I have two. Okay, now I have to decide the same things again. Who's next and where to place it? So on and so forth. So these two basic, apparently simple operations, they hide the complexity within that. It's the complexity of the decision process, which is, okay, according to which criteria do you decide who's next? And according to which other criteria you decide which is the position that you want to place it. More to that. So if you use randomness, the criteria is pretty simple, but also pretty dumb because you don't have any sort of capacity to understand if there is a pattern to the decisions, because there actually isn't. I mean, in true randomness, computer has pseudo-randomness, so it's another thing entirely, but, well, very, very similar. But, well, suppose that we are talking about true randomness. Why true randomness is a demeanor to a design process? Because if you arrive at a certain result, you cannot retrace your steps because you have no criteria for how to understand which steps you have taken. Suppose that you arrive to a certain result and say, okay, that's nice enough, but I would like to change it a little bit, not change it completely. I would like to enhance some characteristics and suppress some other. So if you don't have the capacity to adjust a stable criteria, every time you run the process, the result is widely different or not different at all. You simply don't know because every time you press a button, you don't have a constant response. Every time you you give the same input, you don't have a constant response, which is instead the basic for stable design or stable creativity. So ask a musician if he would like an instrument where every time you press the same key, you get every time a different note at random. I don't think any musician would like to play something like that, because you cannot really count on that, but that's not the single keystroke or the single stroke of a piano key that makes the music. It's the capacity to build a pattern, and the capacity to build a pattern depends on the system on having predictable responses to your input, which doesn't mean that the output is predictable. It's that you know that single response will be what you intended, but then it will be able to manage a lot more complexity when that decision is distributed over like 10,000 instances of things or millions. You simply control, I know that is the decision that has been done. So if you see a certain behavior with the result, then you can analyze the result and say, okay, I know exactly which position I distributed in which place. So I can also start to make sense of the relation between my input and the kind of result that I've got. I'm still not in full control of the result, like because of all the consequences of the result because of this complexity that we are building. But at the same time, there is still the possibility to understand why something that has happened because of this capacity to, let's say, tomographically analyze the system. Okay, enough of me babbling. I mean, I like to talk a lot, so every time I start, if you had enough, just stop me, okay? So, coming back to the system, we're going to set as we evolve some criteria, some very basic criteria that you can also manage and control at some point. But also these two choices, so who's next and where I'm placing it, in this system, they actually get reversed in terms of priority. So the first thing that I have to choose is where am I placing it? Because according to this decision, then this decision has an influence on what am I allowed to put there. Because let's consider this simple object, okay? Remember, there are two types of handles. So according to the type of handle that I'm choosing, I will be allowed to put some kind of objects or not. And also, this will be dictated by my heuristics. Why is the receiver first in the heuristics? For this reason, because first I say, okay, now I place this one, which is the type stick. The type stick has this possible combination in my heuristics. So according to the criteria that I will use to make my decision, once I have decided the location, and that location is a component of the type stick, the next thing that I have to do is, according to a certain criteria, select all the rules that apply to my stick component as a receiver. So depending if, okay, now I want to select, the second criteria will be to select a handle, because maybe I want the handle that is closer to a certain position. So if this handle is selected, then here I can attach another of these guys or the other kind of component. But if the choice falls to one of the extremities, the only possibility is another one of these guys. So you see why the first thing that the system will do is to select the spot where he wants to put another component in. And then it will consider among all the possibilities, all the possible components and instances that can fill that position, it will consider according to another kind of criteria, which one is the next one in my iteration. Right now, in this very simple instance, both of these criteria are random. So let's see a little bit all the parameters that we are using in this definition and familiarize a little bit with this. So the first three part here, so ignore this or, it's just to control the visualization afterwards, but the three that are important for you are these ones. So there is a go toggle. So the go toggle is a continuous go. If you double click, the system will start building and building and building and building until you double click and stop it. Reset allows you to reset the system to the initial state. Step is it's very important because it's actually, I think it's the mode that I suggest you use more often. I mean, go is like, okay, I'm really happy with the settings, I'm really happy with everything, I just want the system to go and go and go and go, then I hit go. But while you are testing the system, my suggestion is that you use step. Because with step, you can go and step forward each time you press it. So if you put steps to 1, you can really see this, how the system goes step by step. So let's see, I've done my first step. What is all this pink junk around here? So the component outputs here, this output, which is tobj, stands for temporary objects. These were all the possibilities to attach something in the position that the system chose. Among all these possibilities, if we hide this preview, it chose to place this one, because then among all the rules, it chose at random. And then when it chose at random, it chose to, this guy was the choice. When you have a criteria which is not randomness, then among all these possibilities, the system will choose only the object that will meet the criteria. And these bunch of possible objects, you will see that it will get thinner and thinner as the assemblage grows, because then you have more and more constraint in your assemblage. The more components you put, the more your options are constrained. So when you step forward, you see that according to which position the system is going to take, because of the heuristic setup. It depends also on the heuristic setup. But so you see the component goes forward, and right now you should be able to see white components and some sort of light green components. What is the difference? The difference, we'll look also at the visualization modes later. The white one are the one who have at least one handle still available. And the light green one are the one that have already been fully occupied. So they are not available for growth anymore. So to be able to see if there are available components allows you to detect if the assemblage stopped because the system is full or for some other reason. So right now, I mean, the number of steps, you can regulate it. It can be 1, it can be 100. So when the number of steps is how many iterations the system will perform every time you press step. So in this case, it placed 100 components at once. And still you can see what are in the last iteration, what were all the possible choices for the last option, the last location it chose for growth, and how the system did grow in the meanwhile. Max component sets a limit for the maximum amount of components that you want in your assemblage. And now it's set to 10,000, but you can really create your own limit. Internally, there is no limit. I mean, the limit is just the computational power of your machine. I've set it to 10,000 just to not make it think forever or get stuck. Because I'm just in the testing phase. In the end, I mean, there is no prescribed maximum amount of components. This is here just as a fail-safe mechanism. Your maximum number of components is just the limit of your computer and where you see your system that you're designing gaining its sort of autonomous expression. So if you think you want to try what happens when you go to I don't know, 100,000 components, if your computer can take that, why not, right? So here is the assembly object set that you get from, as usual, the building the set as we did before. Here is the heuristic string that should be in this format. There is a heuristic mode. Right now, leave it always to manual. Because then this input, heuristic string, is actually a list input, which means you can make a list of more than one heuristic. And then you select with current heuristics which one you want to use. So the index here is just as the assembly object set depends in the order you've put the heuristic string in the list. So if you use more than one, that will the index will be the index of the list. Since we have just one string, the index should be 0 because there's only one element in the list. And these are the two selection criteria. Like I said before, the first thing you do, you select where you want to grow from. So you first of all, you select the receiver. Which one in the assemblage is going to be the next receiver? And right now it's random, but you have a couple of options. One is the Scalar Field, and there's another one with the sequential rule that for whatever reason is still buggy, so don't use it. I'm still, like I said, I'm still working on this thing. Right now, so you have two options, random and using a scalar field. So according to the values of the scalar field, is going to select the component that it's closer to a certain threshold that you can input for the scalar field. And then you can, we'll see later on how to shape the field and how the field is done. The field option is pretty flexible because then you can generate a field from expressions, from objects, from attractor points, from a lot of things. And then you just have to set the threshold that you want. I'll show you what happens when you set the threshold. And then the other one is once you selected the receiving component, there's a criteria for selecting the rules. So when you select the receiving component, the system internally already filters the rules according to the type of receiver. So if the receiver is the component number 0, just the rules, the stick, so just the rules that begin with stick will be part of the options. If your next receiver is going to be an L, then only the rules that have the L as a receiver will be considered. And among those, then you have, in this case, like 3 options. The sequential is still buggy, like I said before. The scalar field, as before, so not just the component that is closer to the threshold value that you input, but also the handle of that component. So suppose you chose this one because it's closer to the threshold. Maybe the threshold is here, or maybe the threshold is here. So when you select the handle that which position is closer to the threshold value will be selected. So it tends to stay closer to the threshold that you're given. Another criteria that I'm going to show is the vector. So the vector will compare the component direction, the receiving component direction, that vector that we input when we were building the component, with a vector field. and actually use the option that will align better to the vector field in that position. So just to let me show you a little bit one thing so that it's actually clear what these options do. So if the field, yeah, let me do that. So this is one application of the field. So this assemblage had like random criteria for deciding the receiver, but it's actually vector driven when selecting the rule for what rule to apply. So in this case, I was testing just a benchmark field, which was half horizontal vector and half vertical vectors. And as you can see, just using the stick, because it has a very obvious directionality in this case, in the part where the vector is horizontal, it tries to keep the things as horizontal as possible. And in the part of the vertical, it tries to keep the things as vertical as possible. Since I was using only the sticks and due to their limitations, sometimes, even in this part, he had for the transition to start placing this other horizontal parts. But then as soon as possible, it switches to verticality. So this was a very simple benchmark test that was done. This was another one. But you can see how the two parts start taking a very, very different identity just according to the directionality of the environment. Okay, now P and S type are the starting point and the start object type. So every time you want to start again or maybe change the heuristic string or the object set, you have to reset and restart the assemblage. And same thing every time you change something in here. So this point is internalized as well. So you can say, I want to start from here and I want to start with the object type 1, which is the other one in my set. Now I have to reset. And then I would start in this position with the other objects. And when I hit step, I will see how my assemblage goes. Due to the fact that the L has a lot more rules in his favor, you will see that it tends to appear more often. So let's start with the object type 0, just for convenience. And let's load another set of rules. So instead of the full heuristics, let's load this one. It's the full, but with the self-C filter activated. So you see that there's a considerably fewer rules. So if we reset, remember that every time you change the rules, you have to reset. And we try to hit step. You see that the assemblage stops at 2 components, and they are both already fully occupied, which means there is no other possibility for them to grow anymore. Now, the first time that I tried this, I thought there was a mistake in the algorithm. There was a bug that I missed somehow, because, well, no, look at these many rules. It's impossible that they get occupied so fast. But if you think about it, instead, it's exactly how it should be. So this is one of the many examples that you might find of how the limitation in those rules, if you put certain limitations in the design of the components and in the rules that you pick, you might end up with a system that have a very short breath in terms of expression, which means they stop too early in the process, because then they run out of options really quick. This is also why I wanted to have a visualization that was telling something about the occupancy of the component. So that when a component is saturated and has no other possibilities to grow, you will see it. So you actually try to analyze and make sense of what's happening. If I didn't have this visualization, I would seriously think that there was something odd or wrong in the process. But no, the process is okay. It's just that the shape of the constraint and the shape of the components that we've put into place determine the fact that this debacle, if you want. So if you try with the other set of rules, remember you have to still reset and step forward. This time it stops a little later, but it's still, it doesn't matter. You can reset any number of times. You will see that you will never exceed a certain number of elements. The configuration might be different, but at some point you always end up with one L component surrounded by 4 or something stick components. Because these rules only allow this kind of combinations. And then you end up, you start to end up your options pretty quickly. So there are some considerations that fall into both the design of the component and the design of the rules that needs to be considered. Of course, this early stop is mainly determined by the design of and the limitation of this guy here. Because there is only one handle which is compatible with the other component. So your options for assembling things are for assembling these two together, or to go from this one to this one, or this one to this one, are pretty limited. In terms of connection, there is just one possible connection in this component to this one. So one of the solutions could be adding more handles all around so that you have more possibilities for them to assemble together. So you can also go around and explore the rest of the rules and see if you see some of the limitation or understand why certain things are happening in a certain way. And I would encourage you to explore, or maybe if you want to also start changing something in the design of the component, maybe adding, removing some handles, and try to make it to familiarize with the definition. Before I let you do that, though, I just wanted to explain a few things in the display department here. What happens after the component? So I will explain more in detail what happens in here, but the things that the most important part of the output is this one, which is the assemblage, which is basically just a list of assembly objects. So let me just switch back to the full rules and have a bit more, an assemblage a little bit more extensive. So you have just a list of assembly objects, sorry. And here, there is a list of the indexes of those objects here in the assemblage who are still available, the ones that are visualized in white. Here you have a counter that tells you how many pieces you have in your assemblage. The iteration, basically, if the assemblage is not saturated, every iteration results in at least in one component being added to the assemblage. So if you have a step set to 100 step, every time you hit step, 100 component will be added more. So if I hit step, the next, if I hit step and I look at the counter next, it should say 201. Yep. There is also one thing. Sometimes you might hit step and nothing happens because there is a fail-safe mechanism inside due to the fact that due to the fact to how Grasshopper manages actually mouse button events. It's a kind of a technicality, but sometimes if you have a high number of steps, so you let the component perform a very big number of loops, the computation required for that might slow down the sensitivity for Grasshopper in capturing the fact that you have actually pressed the mouse button and released the mouse button. So it was happening to me sometimes that even if I was using step, it basically stayed stuck in the step pressed state, and it was going on computing forever. So I had to block that. So step goes, let's say, the first time it performs one step, the second time you press it, it goes blank, just to avoid getting stuck. So you're sure that if nothing happened, press again. Long story short. So this assemblage is then, we extract two things that we need, which is the geometry. I'm calling it coarse geometry because it's like this coarse wrap-up, sort of a bounding that you have to do for collisions. And then the object ID. This is because you have several visualization modes. The first one is just the objects themselves. So all same color. Then by occupancy, the occupied are light green, the saturated, sorry, light green, and the available objects are white. Then you can see them by type, and you can control the color by type in here. Actually, this is one of the inconsistencies I need to fix, because it should be, let's say, this is the one that corresponds to the first object in the merge here. So the color in the merge component should exactly match the order of this other merge component. Okay, so the first color will be associated with whatever first assembly object is here, the second here. If you add more, if you have a third object, then you should add the third color in here, so on and so forth. But this allows you to see the amount of object by type. And you can see that there's a spectacular difference between the type L and the type stick in terms of numbers. And the other is by sequence. So you have a gradient from black to white, passing shades of blue, that tells you which is the oldest and the youngest object in the assemblage. Black being the oldest and white being the youngest. So it's actually a way to trace if there is a criteria or a pattern that you want, that you can see it met or not. If the system starts showing preferences for something, it allows you to peek into the chronology of the assemblage. Or you can avoid having any preview at all and just show nothing. I'm going to keep it by occupancy. It does something, so the clusters are not protected, but they're there for visual syntax. Okay, so if you want to peek into a cluster and see what's exactly going on down there, you can just go into each and every cluster. But I suggest that do so only if you're certain of what you're doing. Otherwise, I mean, you can look, but try not to change anything if you're unsure. If you're actually confident in what you're doing, you can even go and modify things at your own preference. And this is just for visualizing things in a nice, clean, and pretty way that also works with the rendered mode. So graphically, I also try to keep things as seamless as possible. I mean, for the final outcome, I don't pretend to have like so many, let's say, super polished or super curated visualization, although they won't hurt at all. I mean, I like them, but I would like to all of you to focus as much as possible on the design part of the things. So having this sort of capacity to even just export some screenshot from Rhino as a graphic. To me, it's all good. So if you can do that, or anytime you can do that, it's also nice for you to be able to take pictures or anytime record the progress of your actions. So you can build up some deliverables that speak about the progress that you've done. We're gonna talk about the project and the deliverables probably already tomorrow or on day 3. It's gonna be a very, let's say, limited and simple project, also because there are different phases to it. And I'm gonna be more explicit starting tomorrow about it. But for the time being, since it's almost 5:15. I will say that we can take a break now. And also I will leave you some minutes to explore this thing. So we can also take, all in all, a 30 minutes break, although I'll be back in 15. So, I mean, let's have like 15 minutes break, and the other 15 minutes is left to you to explore this thing, move things around, change, tweak it up, hopefully not mess it up, but yeah, to play around. So right now, I'm gonna just put some sort of pause screen, which is gonna be just a cover of this. Ooh, someone's chatting, yep. Ooh. All right. Okay, let's have a break, and I'll try to. Okay, guys, we're on a break.
Cool. See you later.
Andrea, can you hear me?
Yes.
Okay, let's see if I can. Can you share your video with the Grasshopper screen so I can take a look at things?
Yes, I was trying just to reconnect the components in any case. Share screen. I cannot share it because you disable the share.
Yeah, just wait a second. I'm trying to.
Okay.
And oh man, because I'm used to the hold it. I'm used to the application on the iPad, and the options are all out of place here. I have no idea where's this. Where is the thing? Ah man. Does any or where I can give the participant the possibility to, oh wait, probably here. Let me see. Can you see my request now?
Yes.
You should be able.
Am I sharing?
I don't see it in my Zoom window.
No, okay. No, I was disable attendee screen sharing.
So, right, there it is. I found also where, okay, I can make you co-host.
Do you have a Zoom account?
Thanks.
Because then I will help all the Zoom meetings.
Yeah.
I will just make one. So what I normally do is still have one room for the talk.
This one.
It always stays the same.
Okay, now I'm seeing your screen. Okay, right click in the red component. Yeah, manage assemblies.
It's already here, but
Is that yeah? Okay. Yeah, hit reset. Okay. Yes, hit okay. Hit reset.
it
Reset.
and then I can
Reset. Yeah, there.
here.
Yeah, not go. Reset.
Ah.
Whoa, that's weird.
I tried
Can you show me the output?
Yes.
Excuse me. Hi, Alicia.
Yeah.
I had the same problem, and when I upgraded to SR27, it helped me.
Okay, just show me the.
Yeah, but this is.
No, not this one. Not this one. That's fine. Put a panel outside of the out of the red component.
Okay.
Let me see that error message. Yeah. Type of namespace. It seems that it's not. Wait. Is the DLL blocked? By any chance? Go to the Grasshopper libraries. Yeah, right click on assemblies DLL.
Yeah.
Properties. No.
It's locked, unlocked. There is no.
That's incredible. That's weird.
And if I open the DLL check, it works.
No, okay. I think it works because that is, well, that is
Isn't
really.
it because you're on Windows 7?
Yes.
I never thought about that. The operating system could have a problem with that, like finding the DLL.
Or maybe check your Net Framework version, I don't know.
Is your Net Framework above, but you told me it was above 450, right, Andrea?
450.
That .NET Framework. Remember, I sent you a file to check. No, Rhino is okay.
No, Rhino is okay. No, I don't remember, but it was okay when I checked it.
Okay. Can you double click on the red component?
Here.
Yeah. Let's open the C# editor. Make it a bit larger. Yeah, it's using the assemblage. Well, no, that part is looking good to me, but somehow it's not reading the assemblies DLL. Do you have the latest version of assemblies DLL?
Yes, and I tried also to substitute it with your own just to try. Just to try, but it didn't work.
I have no idea why this is happening.
No, I tried to install every kind of version.
No. I understand. It's just that I have no idea why this is happening. Who is the other person who had the same problem?
But I don't want to waste.
No, don't worry. I mean, we are still in the break, so I mean that's the right time to do this. So I'm just sorry that you're missing something. Now until like 3:45, I mean, you have time to play around if the system works. So in this case, I can be of assistance. It looks like the only thing I can think of is that your .NET version is not actually above 450.
Okay, so maybe let me...
Do you remember the tools that I sent to verify the .NET version?
It was this one.
Yeah. Oh, no, yeah, it's above 4.5.
Yeah.
Yeah, so... Are you running parallels?
Yes.
That's the problem.
Really?
Yeah.
From tomorrow, I'm gonna have a new computer here in the studio. Usable.
I believe that. I strongly believe that is the problem.
Okay.
Because yeah, it could be a problem of parallels.
Sorry, for tomorrow I'm gonna have a computer.
Yeah, no, I mean that's also the thing. I mean, there are things. Working with this, I mean, if you do custom stuff, thinking about all the versions, all the things, it's a nightmare because there's always something that doesn't work. So I was just asking for the configuration that I was sure worked with what I was building. Okay. But yeah, no, I'm sorry. Yeah, I guess you'll just have to follow along watching for today. I'm sorry.
No, it's my problem. Don't worry. Okay, I'm gonna stop sharing.
But it's good that you asked me in the break time, so we could do this.
Okay, but just to say, do I have all the plugins needed here in the top bar? Just to
it looks like it looks so to me.
Yeah. Okay.
So user should contain the user tab at the end should have the preview component. Yeah, exactly.
Okay.
Yeah, for just user objects. No, I mean you should have everything.
Okay.
But it's weird. It's weird that, for instance, the weird thing is that it's not just a couple of classes do not
appear.
Where the field and the mesh environment. So the field is that all the error message, right?
Yeah.
The one in the panel. So it's not recognizing the field and the mesh environment.
Exactly.
Go into the Grasshopper libraries folder. Just a second.
Yeah, I checked.
Because it seems like.
But they are inside.
No. I know they are inside. I just wanted to see the date on that. Libraries.
Yes.
Oh yeah, you have an old version. That is really? From 21 June. The latest one is 28 June. That's the problem.
Because when I tried to download some version, it was like an expired link, so I didn't know if I made a.
No. I mean the mail that I sent this morning. I sent a follow up because the link was I forgot the link was restricted. No, your problem is not parallels in this case. Is that you have an old version of the library. Just update assemblies DLL and you should be good to go.
But it's the material zip. Is the
Sorry?
material?
No. The assemblies.zip. I send. If you look at your email from my account of DigitalFutures, I sent like there are two emails. The first one with the material. The second one, oh no, it's not the material. It's assemblage. You should look for the last one with assemblage. But the link is the same. The link is the same. I mean, it should be the same link. Otherwise, I'm gonna send the link now in the chat. No problem.
Okay. The link that you sent us today in the morning was actually with an older version of assemblage than yesterday.
Oh, really?
At least it says me, so I didn't upload it today.
Oh, really?
It says me that it's from 26, and yesterday I downloaded it was 27. I don't know.
Well,
yeah, it's the same for me as well. Wow.
Wait, something weird is happening. So, wait a second. I'm just gonna package the version that I'm using from the Grasshopper libraries. That's wow. Yeah. I'm sorry, guys. I think I messed up something because I'm too tired already.
But it still works, so.
No, it's okay. It's fine. It's fine. Don't worry. I mean, just. Also, because now you don't need to. You don't need a DLL check Grasshopper file anymore. Okay, so I'm gonna copy paste the link in the chat right now, so that everybody has it. Provided that I found where the chat is, because man, where the hell is the chat right now? Ah, no, it's right here. Sorry.
That's it, right? That's it.
Yeah. In the chat, you should have the link with the updated version of assemblage. This is from, June 27. That's the one that I'm using.
And at one point, we all have lunch together.
Anyway, I will perform a check tonight and maybe have an updated version tomorrow. But for the time being, this should work for everyone. I mean, if your works, don't change anything. Did you get it, Andrea?
Yes.
Okay. You have to restart running Grasshopper, but then you should be good to go.
Yes.
If no one comes, I mean, they come to the meeting. They want to have a party at the opening.
Sorry for the mix-up. So, okay. So I'll leave you 10 more minutes to do your explorations and stuff. So
I have this weird problem when I copy the assemblage file that you gave me. It, I mean, it's perhaps just a display problem for Windows, but like when I copy it, it says the date, it changes the date automatically to 27/6.
No, the new assemblage is dated in 27/6.
Yeah, genau. But when I copy that, it's strange. It's just
What?
Take back the 27/6 when I copy it at that position.
It takes a, what do you mean?
I mean, the date modified, it says that it is saved on 27/6.
Because I think that's the date where I saved it. I'm still using that.
Okay, all right.
No, I didn't save it today. It should be okay. It should be like that.
Right.
Sorry, was it Shermin that asked me if we could record the videos, right? Shermin,
Yes,
was that you?
me. Yes,
I found where the freaking option is.